So in this video, I want to talk about chapter 9 in regards to R. So chapter 9 is about hypothesis testing, and chapter 9 starts with the one mean z-test. Now, in actual data science, when you do hypothesis testing and inferential statistics, you're not going to really know the population standard deviation. You really only know the population standard deviation if you have every piece of data, right? If you have the entire population, then you can talk about the standard deviation in that way. But if we are doing inferential statistics, then the idea is that you're taking a sample and you're studying the sample instead of the population. And so most of the time, in fact, I don't want to say all the time because that seems fraught with, I don't like dealing in absolutes in that way. But the vast majority of the time, you're not going to know the population standard deviation. And it's to the extent where R doesn't have a z-test built in. R does have a t-test. So if you don't know the population standard deviation, you're using the t-distribution. R does have that built in. That does come up very frequently. But oftentimes you just don't know the population standard deviation. So the point of what I'm saying here is that R does not do the one mean z-test. You just have to use R as a calculator. There's no way around that. That's going to be the case for chapter 9. That's going to be the case for chapter 12, which we'll talk about later. You just have to use R as a calculator, and there's nothing to do there. So when I say that's the case for chapter 9, I mean specifically with the z-test. There's also the one mean t-test, okay? And so that's going to be used when you don't know the underlying population standard deviation, and there is a lot that we can do with R there, okay? So there's still a few things that we can talk about with R. What I thought I would do for these chapters and for later chapters is to go over some problems. And so I decided for chapter 9 to go over some of the homework problems and to show you how those work. So I want to look at questions 10, 11, and 12 or so. And so here, question 10 says we want to find the critical values for a one mean z-test. Okay, one mean means that we just have one population that we're studying. We'll talk about two means later. So that's what chapter 10 is all about. But the one mean z-test just means that we have one population. And we want to find a two-tailed test with alpha equals 0.09. So the fact that it's two-tailed, what that means, and let's just kind of go over this picture here. So we're going to take our total area alpha, and we're going to split it up into two pieces so that the area added up between those two pieces is alpha. So if our alpha is 0.09, then our alpha over 2 is going to be 0.045. Okay, so if I just take 0.09 divided by 2, you get 0.045. And then I want to find the critical value, the z sub, in this case, 0.045. And so the way that I would do that is I would just take p norm of 0.045, and that would be, excuse me, not p norm. I'm thinking of q norm of 0.045. That'll give me the critical value. And so this will be negative 1.695 and positive 1.695. So remember that the q norm value, this will give you the cutoff point up to which the area under the curve is 0.045. And then we have a matching one over here because it's two-tailed. Okay, and so the critical values, if we want to round to 2 decimal places, we could actually make R work for us that way as well. So if you want to figure out what this is rounded to 2 decimal places, you could just do it that way. So we get negative 1.70 and positive 1.70. And again, we have 2 critical values because it's two-tailed. Okay, and then we can look at the picture to match. I don't care about that part. If I were to have a left-tailed or a right-tailed test, we'd have to do this slightly differently. For a one-tailed test, what you do is you do not split the area in 2. You just, the area, if it's left-tailed, you just want the area to be alpha. If it's right-tailed, you want the area to be alpha, right? You just don't split it in 2. So if I want to have a left-tailed test and our alpha is, I lost the question here, sorry. Our alpha is 0.02. Then what I would do is I would just go to R and I would just very simply type in p norm 0.02. If I want, I could round it to 2 decimal places. I better spell the word round correctly. And that would give me the answer. So our, and again, I did this p norm thing. Sorry, you use q norm to find critical values. So it'll be negative 2.05. Okay. And then again, you can match it with the picture. If it's a right-tailed test, then you could do this one of two ways. I think it's easiest just to do it this way. So I like to take 1 minus alpha and find Q norm of that. Again, we're going to round it to 2 decimal places. We get 1.28. Okay, so I think that's one way to do it. The other way you could do it is you could do 1 minus Q norm 0.1, again, rounded to 2 decimal places. So if you do 1 minus that, then, oops, and I did this again. I'm sorry, not 1 minus, just minus. There we go. 1.28, okay, because we're getting the negative value. So the reason why I put the minus in front is that if I'm looking for this value over here, by symmetry, so if I want to have 0.10 over here, I can figure out what's the value over here that'll have 0.10 to the left, and then I just take the negative of that to make it positive. So in this case, it becomes 1.28. Okay, so that's the way that you could do that. And that's really all there is to finding critical values. You just use the Q norm function, plug in the alpha, and then you just have to remember that if it's two-tailed, you take alpha and divide by 2. And that's because of the picture here. And if it's one-tailed, you do not take alpha over 2. You just have alpha because you just have one single region. Okay, and so that's really all there is to that. Now, on the flip side, remember that there's 2 approaches here. I'm way zoomed in here to get a good view here, but there's the critical value approach and the p-value approach with hypothesis testing. And with the critical value approach, you're just comparing your test statistic to the critical value. So there's not too much more to it than we've already talked about. For the p-value approach, what you want to do is you want to calculate the probability that your data that you obtain from the sample is at least as you want to calculate the probability that a random sample is at least as extreme as the data you obtain. That's what the p-value is. And if your p is less than or equal to alpha, then you reject the null hypothesis. Otherwise, you fail to reject the null hypothesis. And so you can use this to find the p-value of data as well. And so if you have, let's say, a standard normal, let's go ahead and let's find a problem where we have to find the p-value. So let's say I have a test statistic of negative 2.46. It's a left-tailed test. I want to find the p-value of this data. What I would do to find the p-value is I would use the p norm. And so I would do p norm negative 2.46. Now, I do not need to do anything else to this. This is just a left-tailed, it's one-tailed test. Our p-value that we're going to get is 0.0069. Okay, so if we want to round to 4 decimal places, that would be it, 0.0069. That's the p-value. It's less than 0.01. So that means that we would reject the null hypothesis. Okay, and that's how we find the p-value, and that's how we find the q-value. Now, the only other thing that I can add here is that if I wanted to find, and I'm not sure I have a problem like this, but if I wanted to find the p-value, let's say that I have a test statistic of negative 2.46, but it's two-tailed. Okay, so if I wanted to find the p-value there, what I would need to do is I would need to compute. Let me go back to the picture just to show you what I'm going to do. If I want to find the p-value, I would need to find the area to the left of this test statistic and also to the right of the positive test statistic. So I would want to find the area to the left of negative 2.46 plus the area to the right of positive 2.46 and add them together. By symmetry, these areas are equal. And so what you could do there by symmetry, if you wanted to find the p-value of a two-tailed test, is you would take 2 times p norm of negative 2.46. That would be 0.01. And so then if we were having a significance of 0.01, then we would fail to reject because our p-value would be greater than alpha. And so that's how we would use this to find the p-value. So you use Q norm to find critical values. You use P norm to find p-values. Okay, so I hope that that's clear enough there. So what I want to do next is I want to talk about using R to solve some problems in regards to the test statistic, the t-test. And so here, this is going to take a critical value approach. And let's do one where we do the p-value approach. So this is problem 21. Now, the way that these problems are written, they give you the sample mean, they give you the sample standard deviation, and they give you the sample size. Okay, and so they give you these values over here. That's supposed to make it easier for you to use a calculator to come up with the test statistic. But if you use R, you would actually rather have the sample, because you could just use the t.test function and then you'd be done. And you don't really have to do anything else there. So what you can do is you can kind of recreate a sample with the prescribed statistics that you like. So if you want to come up with 15 numbers with a mean of 24 and a standard deviation of 8, what you could do is you could use R to come up with a data set like that. And so you just pick any random numbers. I just always use the normal distribution. It doesn't really matter what distribution you use, as long as you're not using the same number over and over, because otherwise your standard deviation will be 0 and this trick will never work. But we just take 15 random numbers, and I had to run this. So I got 15 more random numbers because I forgot to save it as a data set. But you want to call X your data set. And then what you're going to do, and I'm going to explain this to you kind of in 2 different ways, and we'll do it slowly, and then later I'll do it fast. But the first thing I want to do is I want to take all of the values. And first, if I look at the data set X, there are 15 random numbers from a normal distribution. And so they're going to fit nicely in a bell curve-ish. Okay, they're not going to fit perfectly. They're going to be kind of close. But they're just 15 random numbers from this set. So they're going to be skewed one way or another. So the mean's not going to be exactly 0, but it'll be close. In our case, it's negative 0.05. The standard deviation is not going to be exactly 1, but it'll be kind of close. So in this case, 1.13. And so what we want to do is we want to take our data set X and make it so that it has a mean of 0 and a standard deviation of 1. And then that's going to allow us to scale appropriately. And so here's how I'm going to do this. And I'll again kind of explain this. Don't pay attention to the codes that I use yet, except that I'm going to subtract the mean, and I'm going to let that be Y. So Y now is the same numbers as X, just with mean 0. So if I type in mean of Y, this is 0 up to 16 or 17 decimal places, which is the accuracy that we can get with R. And then the next thing that we're going to do is notice that the standard deviation of Y is going to be the same as the standard deviation of X, because all we've done is just horizontally translate the data. So this amount that it's spread out is going to be the same. So what I want to do instead is I'm going to define a new variable Z, and it's going to be Y, but divided by the standard deviation of Y. And then what we've done is now we have a data set Z, and we haven't messed with the mean of it. The mean of Z is still going to be 0, basically 0. So again, 0 to 17 decimal places. And it's going to have a standard deviation of 1. Oops, standard deviation of 1. And then the final step is we're going to take Z and we're going to add back in actually 2 things. We're going to add back in 24, and then we're going to multiply all the values in Z by 8. And what that's going to do is it's going to spread out all the data. And then what we have is we have a data set with a mean of 24, a standard deviation of 8, and there should be 15 values. I can't type. There should be 15 values there. Okay, and so that's the process that we're going to use to recreate the data. And now W is our magic list that's going to work perfectly well for our test. Okay, now hopefully I explained each step nicely, but what I want to do is show you how to quickly just come up with this data set. And so you can do all these steps at once. You're going to create the data set X, and then I'm going to redefine X to be itself minus its mean. I'm going to multiply by the standard deviation that we want, divide by the standard deviation that we have, and then add the sample mean that we want. And if I do that, then there's our data set X. And again, this is, because I used 15 more random numbers, it's going to be a different data set than we had before, but it's going to have the same properties. It's going to have a mean of 24, a standard deviation of 8, and there should be 15 values there. Okay, and so now we can use this data set X for this problem. So if I want to compute the test statistic is going to be 11.619. We want to round it to 2 decimal places. That's 11.62. And it's telling me I'm wrong. And that's because I ran the wrong test. So let's think about this here. So our test statistic so we're going to run our test statistic with X. We're going to have a mean of 25, and we're going to have our alternative hypothesis being less. And so our test statistic is going to be negative 0.48. I put in an incomplete code there. And then the p-value, notice that we get that for free. The p-value is 0.3179. So let's see, 0.3179 is greater than 0.1. And then we just have to figure out what's going to happen here. So it turns out we do not reject the null hypothesis. And one other comment about these questions in chapters 9 and 10, if you reject the null hypothesis, it's because you have sufficient evidence to reject it. If you do not reject, it's because you do not have sufficient evidence to reject it. And so in this case, we do not have sufficient evidence to conclude that the mean is less than 25, because that's our alternative hypothesis. Okay, and so that's always going to be how that works as far as those go. I do think that it's worthwhile for me to go back and just to look at question number 20. So question number 20 is basically the same. We have a data set. We want to look at the test statistic and the p-value. This one's kind of silly because the mean is 20, the sample mean is 27, and the population mean is 27. And so our test statistic is going to be 0 because the formula for it is going to be x bar minus mu divided by stuff. And so we're going to have 0 in there. So anyways, that's how I know that the test statistic is 0. But just for more practice, if I wanted to come up with a data set, here I have 24 numbers, but I want to come up with a data set with a mean of 27, a sample mean of 27, and a sample standard deviation of 7. What I would do is I would redefine x to be x minus its mean times 7 divided by the standard deviation that we have, plus 27. And then we could run the t.test function with x. Our mean is 27. And then this is a left-tailed test. So our alternative would be less. And then this is going to run everything that we want. So of course our t is 0. Our p-value is 0.5 because our test statistic is exactly on the mean. And so if we want to find the p-value, that would be 0.5. That's just the area to the left of our test statistic in this case. And then we can find critical values here. So if we want to find the critical values, we'll do the same thing that we did before. We would use the Q function. In this case, we're going to use the QT function because it's the t distribution, not the normal distribution. And so we're going to do QT. We're going to look, let's see, our alpha is 10%. We have a left-tailed test. And so we're going to have a negative value, negative t sub a. And so let's see, we're going to have QT. Our P is going to be 0.10. We're going to have 23 degrees of freedom because we have 24 values in our data set. And that's going to give us our test, our critical value of negative 1.319. Okay, so that's going to be our answer there. So negative 1.319. And then at the end, you would interpret just like you would before. Okay, and so with the t.test function, always remember that you have the help component here, but with the t.test function, you really only have a few things that you need to worry about for now. You have this t.test. Your data set's going to be X. We'll worry about Y in chapter 10. Don't worry about that. And then your alternative hypothesis can be less or greater. If it's two-sided, you don't need to put anything in at all. And then mu being whatever your population mean is. And then you can change the confidence level as well. Okay, so if you wanted to change the confidence level, if you're doing if you're trying to do a confidence interval, then you can mess with that as well. Okay. But that's really it for the t.test function. So if I think anything else to share, I'll do it. Otherwise, I think that's it now for chapter 9.